Hello, everybody. In the warm-up, we evoked the idea from Algebra 1 about what growth looks like for linear functions and for exponential functions. So for linear functions, if you look at how the y values are increasing, if the y values are increasing at a constant rate, if the growth is constant, you know that's characteristic of a linear function. Not only that, but the growth actually tells you the slope of the line. The other thing from Algebra 1 is if the y values are increasing by being multiplied by a constant. So if you're multiplying by 3 every time, for example, that's exponential growth, and that tells you the base of the exponential. Okay, so we're going to extend that. The theme of today is, well, okay, we got linear growth. How could you tell if it was quadratic growth? How could you tell if data was cubic? How could you tell if it was something else? So if you just look at the graphs, this is the graph of a squared and a cubed equation, and they look very, very similar. So you can't really tell if you're just looking at the graph. You have to dig into the pattern of the actual growth in the data. So I invited people to pause, you can pause the video, but in class I invited people to try and just see what they notice. Like, what do they notice about the growth here? What do they notice about the growth there? And people said, well, look, I see that the y values here are increasing by 1, and then 3 to 8 is 5, and then 8 to 17 is increasing by 9. So it's like the y values are not growing by the same amount. Like the growth is increasing. So that's why we look at the second order growth. Second order growth is saying how much is the growth growing. So here, to get from 1 to 5, that's an increase of 4. To get from 5 to 9, it's also an increase of 4. So the first order growth is saying how are the y values growing. The second order growth is saying how is the growth growing? How is the growth of the y values growing? You can actually see that in this graph of the quadratic down here. This is just y equals x squared. But you can see these growth triangles here. I go over 1, up 1, over 1, up 3, over 1, up 5. So you can see that the heights are growing. And if you ask, well, how much are they growing by? You can see that the heights are growing by 2 every time. So that's the meaning of second order growth. And if your data has constant second order growth, that means it's an x squared equation. You can probably guess what's happening next. For a cubic equation, an x cubed, the first order growth is increasing. And the second order growth is also increasing. But then if you look at the third order growth, so how much is the second order growth growing by, it looks like that's increasing by 6 every time. So again, we've reached a constant growth. So if you're going to write down some takeaways, it could be this. It could be linear functions have constant first order growth. Sorry, I'm sort of tilted here. It's coming out poorly. Quadratic functions have constant second order growth, and so on. An x to the third equation has constant third order growth. You will probably guess an x to the fourth equation has a constant fourth order growth, and that's all true. Just as a side note here, we didn't actually prove that. I'm just telling you that it is true. This connects to a much deeper fact about functions that you'll learn in calculus to do with derivatives. Sorry, I should say one more thing before we do the bottom. Why am I telling you all of this? The practical upshot is that if you have some data and you want to know what's the equation, if you can look at the growth and you can say, oh, I see that the third order growth is constant, now you know that it's going to be a cubic equation. You probably won't know what specific cubic equation it is. You'll have to write a general cubic equation, but at least you know what kind of equation you're dealing with. And then as a next step, you could start to figure out what specific equation is it. Okay, so let's go down here to exponentials. So as I said before, in Algebra 1, you learned that this is the characteristic growth for exponentials. The y values multiply. I invited everybody to pause and I asked them, do these values also show that multiplicative growth? Am I multiplying by the same thing to get from one to the next to the next to the next? Why don't you pause it and see if you can answer that for yourself? I'm going to actually reproduce it over here because I want to use that area for something else later. So here's how you could decide. If I have -4, what do you need to multiply it by to get -2? Well, since -2 is just half of -4, if I multiply -4 by a half, I get -2. Okay, so if it were really true that the y values exhibited constant multiplicative growth, I should multiply by half again to get the next one, but I don't. It doesn't work. -2 times a half would give me -1, not 4. So what that shows us is that the y values don't have this multiplicative growth. But here's the problem. The problem is this actually is data from an exponential function. So they didn't quite lie to you in Algebra 1. But when they showed you this pattern in the growth in Algebra 1, that's only the pattern of growth for an exponential that hasn't been transformed at all. So let's do something else. A lot of students, when I ask them to look at the growth, do the same thing. They look at how are the y values increasing. So they're figuring out what do you have to add by. So 1 plus 2 gets to 3, 3 plus 6 gets to 9, 9 plus 18 gets to 27. And you might notice now another pattern. Now we do have multiplication by 3. So I want to give you a way of interpreting what are these numbers about. These numbers are literally how much do the y values increase. They're the growth of the y values. So these numbers describe the heights of the slope triangles, the growth triangles. So here, as I go from an x-coordinate of 0 to 1, the y-coordinates go from 1 to 3. So that little sliver there is +2. And then this here is +6. And then this here is +18. Okay, so just like this one up here, we saw that the growth was growing. Here, you can see that the growth is growing, but the way that it's growing is by multiplying by 3's. Let's look at the same thing here. So here, if I'm going to add something to -4 to get to -2, it's 2. To get from -2 to 4, I add 6. To get from 4 to 12, I get 18. So again, if I was going to graph this, you would see those growth triangles growing in height. And they're growing in height, and their heights are growing by multiplying by 3 every time. So whenever you see the heights of the growth triangles growing by multiplication, that's how you know it's an exponential. So the y values might not be, but the heights of the growth triangles will be. That's it. So recapping, if you have some data and you want to know what's my family of equations, you can look and see, look at the growth and the growth of the growth and the growth of the growth of the growth and ask, when does it reach a constant? And if it ever reaches a constant, that'll tell you you have some kind of polynomial. Linear function, x squared is quadratic, x cubed is cubic. Or if you look at just the first order growth triangles and they have a multiplicative growth pattern, then you can know that it's been a shifted exponential. Oh, one last note. I asked second block if they could figure out how it's been shifted. It's a shifted exponential. And somebody realized from the warm-up, all exponentials go through the point 0, 1. And that was from the warm-up. Remember when we graphed 2 to the x and 5 to the x? And 2 to the x and 5 to the x both went through 0, 1, because if you plug in 0 for x, anything to the 0 power gives you 1, unless the base is 0, in which case it's undefined. So, if you know this is an exponential, you expect it to go through 0, 1, but it's not. It's going through 0, -4. So what you're thinking is, what used to go through 0, 1 has been shifted down. So now it goes through... Oops. Let's make that -4. Let's make this 1. So now it goes through -4. Therefore, it must have been shifted down by 5. because the multiplicative growth is 3, I know it's a 3 to the x function. So this would be 3 to the x minus 5. Okay, let's do another video.